Problem here, we have a boat. It's traveling along from an island to the shore, okay, or needs to get from the island to point A, and it has a maximum speed along the water of 18 kilometers an hour, but once it gets to the land it can travel faster. It can travel at 40 kilometers an hour. So if we went all the way across here, that would be the shortest distance, but the problem is we're taking the shortest distance, but we're going the slowest we could possibly go because the boat is much slower than on the land. Here, if we go straight across, we maximize the amount of time in the car, which we want to do, but the problem is this is the longest route we could possibly take, straight and across. So there must be some point in the middle here, somewhere in here, at an angle that we can go to minimize the amount of time. Okay, so this is an optimization problem, so we need to know that we need to minimize time. So if we want to minimize time, we need an equation for time. And our equation for time is going to look like this. So I'm going to talk about the time on the water and the time on the land. So T water, this is my T land. So the total time total, is equal to time on water plus time on land. So I need to come up with some expression for time on water and time on land that somehow accommodates theta. Okay, so I needed some variable here. I'm going to actually do this in terms of x. So I'm going to let that be x here. And I'm going to say that the time on the water is going to be the distance on the land, okay, just distance on the water divided by the speed is going to be equal to time. So we know that, I'm just going to draw it out here, time is equal to the distance divided by speed or velocity. Okay, so that should give me my time. So and the reason I'm going to do this for x is I think it's just going to be easier to do this for x. We could do it for theta, but if I find x, I have my triangle here, and I can just find my theta afterwards. So in a problem like this, we can do this directly for theta, or we can do it for x and solve for theta afterward. That's what I'm choosing to do right now. Okay, so my time on the water is going to look like this. The distance on the water is going to look like this. The distance on the water is going to be Pythagoras. It's going to be the hypotenuse of that length. So it's going to be 18 squared plus x squared, square root, divided by the speed on the water, which we were told. It's 18 kilometers an hour. So 18 kilometers per hour. Okay, so then we want to do the time on land. So I'm going to do this a different color. Time on land. Okay, the time on land is going to be the distance on the land, which is going to be 50 minus x, represents the distance on the land, divided by the speed on the land. So there we go. So at this point, I've come up with an equation that I can minimize based on x. Okay, although I want to end up solving for theta, at least I've based it on x and I can figure out theta afterwards. And again, like I said before, you could do this directly for theta, which is perfectly fine if you want to set it up that way. But this may be a little bit easier to follow. So there it is. So there's my function. All I need to do is differentiate this and find out where this derivative is equal to 0, because that would give me my min or max.